So Feng, can you make sure you print out the solutions?
Next class I will print homework 4 and homework 5.
Okay, yeah,
Because homework 4 still have
Right.
late submission. Yeah.
that's right. So you're going to bring like solutions for both homework 4 and 5. So that hope that we are well prepared with midterm. So the midterm exam will be on March 7th. Okay, will include and will include graph-based testing, RPI graph-based testing. So that means both all the homework assignments, including homework 5, will be covered by the midterm exam. And we're going to have a review probably next Tuesday, before the next Tuesday, before the midterm. We're going to discuss more details about it. Okay, yes, I had a typo. We're going to finish graph-based testing today. We have 2 slides left, and we're going to get started with gradient testing. So last time we discussed data flow testing. 3 most important concepts in data flow testing. What is the definition? What is the definition?
Where you give a variable value.
A variable gets a value. What is the use?
Where you perform a computation with that value, with the variable.
Okay. So basically you read the value of the variable. What is the DU part? What is the DU part?
After the definition to where you first use it, or
Okay.
any use.
Any use, but there are 2 specific requirements. Okay. For part from a definition to a use. Okay, to qualify as a DU part. What are the 2 requirements?
Path has to be simple
Has to be simple part, yes.
and depth clear.
Has to be depth. Okay. So these are the 2 key points you have to remember. Okay. When you try to identify your path. Okay. Let's see. Finish the graph testing first. I think that probably missed 1 slide, which I want to talk about now, because that's going to affect your homework assignment. Okay, did we discuss this slide? Probably I escaped this slide for some reason, which I don't quite remember. So we discussed side trips, detours for control group testing. Right? Sometimes we cannot directly tour the path, okay, like the right path. You are going to allow like side trips or detours, right? So you can do the same for data flow testing. Sometimes if you want to try to cover the DU path, that's the test requirements, right? In data flow testing, we try to cover different DU path. So sometimes you have to allow, side trips, detours, right? Because you cannot directly pull the new path. Okay? It's the same idea here. But what's important is that when you allow a side trip or a detour, you have to make sure that side trip, that detour is definite. Okay? Remember, if it's not that clear, you are not really serving the purpose of trying to cover that particular new part, right? Because you are really not testing the definition that you want to test. So this is something very important, okay? I believe when you work on your homework assignments, you have to keep this in mind. Otherwise, you're not going to get the correct answer. Okay? And again, for the exams, this is also important. When you allow side trips, detours for data flow testing, they have to be definite. Any question on this? Okay. Well, now I remember something, right? I gave you an assignment. Last time, we look at this example, this test set. This you have 4 test cases, right? These 4 test cases do achieve edge coverage, but they were not able to detect the bug behind. Okay, and we discussed the reason. It's really because the incorrect value was never used, right? If you cannot use it, you're not going to know whether that value is correct or incorrect. That is the basic idea behind data flow testing, right? You want to make sure variables have correct values, and to do that, you have to use those values. Okay, that's really the fundamental idea behind data flow testing. Okay, and these test cases cannot detect this bug. Okay, and I gave you assignments. If you remember, can you find the test case that would allow you to detect the bug? Okay. So basically, the bug is in this line, right? It's supposed to be x plus 1 plus z, right? So this is where the bug is. Can you find the test case, okay, that would allow us to detect this bug? Remember, the requirement is that you have to use it, right? The only place that you could use it is this statement, right? This is the only place where the value of y is used and is going to affect the output. Okay, this value is also used here, but it's not does not affect the output. So remember, when you test, you only check the external output. Okay, only debug you go inside the program. So you have to go back. You have to execute the loop at least twice. Otherwise, you're not going to detect this bug, right? As we have discussed before. And you have to execute this statement when you get back to the loop. Okay. Can anyone give me a test case that would allow us to detect this bug? Anyone thought about this after class? We just forgot. So when I'm looking for a test case, it means we want to give values to this to the inputs, right? So basically x, y, and count. What values we want to give to these 3 variables, so that when we execute the test case, it will allow us to detect that bug. So the,
Negative X value and a positive Y value?
right, so you have to make sure X has to be negative and Y has to be positive. When you execute the loop for the second time, okay?
Second time.
Yeah, for the first time, it's not sufficient, right? You have to make sure, because we want to execute this statement in the second time. Okay? So we can do it like one by one, okay? Anyone wants to have some ideas that already thought about it before I tell you what the values are supposed to be, could be, not are supposed to be. There are many different solutions, right? Anyone wants to give a try?
Negative 2 for X.
Negative 2, X.
X negative 2.
Okay, good. Y,
Y 2.
Y2.
Z 5.
Z doesn't matter, right?
Oh, okay.
Z is not an input.
Okay.
Okay,
Okay.
count. 2. Is this what I heard? Okay.
Yeah.
Let's try. Okay, it doesn't hurt to try, right? So -2, when you come here, X is -2, you come here, Y is 2, so you execute this branch. And Z would be -2, 0, Z is 0, the initial value is 0, right? So Z would be 1, right? You come down here, Y equals X times Y, so X is -2, right? Y is 2, right? It will be -4, plus Z is 1, right? It will be -3. So count is 2, so after you execute 15, statement 15, count is 1, you go back, right? That's what we want. But here, X is -2, right? So far so good. But Y is what? Y is -3, right? If I remember correctly. So it's not going to execute this statement. You're going to skip this true branch. You're going to come here, and you're going to re-execute this statement. It doesn't matter, right? Because you're going to get out of the loop. You're going to output the value of Z, which is 1 at here, and that's going to be that's what you would expect. It's not going to help you detect this one, right? Like the reason is that Y became negative, and that's not going to help us to detect this, right? But we can fix it, right? Can you fix it? Remember, we want to execute statement 8 in the second iteration.
Negative 1, 1, and 0.
Negative 1, 1, count
2.
2, 0.
Not 0.
Okay, let's try this one, right? So -1, -1 over here. So this is 1. So this is still 1, right? Because Z is 0. So you come here, -1 times 1 is -1 plus 1 is 0. That's going to work, right? When you come back here, X is -1, Y is 0, so you can still execute statements. Well, let's see. Let's double check. So over here, you execute statement 8, so it would be Z equals Y would be 0, right? So Z would be 1, right? So let's think about if we run the same test case on the correct program. So it's -1, 1 over here, Z is 1, right? So we're going to come here, execute statement 14. It's X plus 1 plus Z, right? So it's -1 plus 1 plus Z. Y would be 1, right?
Y is 0,
Minus
1 plus 0 plus.
1 minus 1 plus 1, right? Did I make any mistake? This is the test case we're trying to run, right? Is that right? So -1 plus the correct program should be x plus 1, right? So -1 plus 1 plus 1 here, right? Z is also 1. So it's going to be 1, right? So when you come back here for the second time, -1, 1. So here is 1 times 1 times plus 1. So it's going to be 2. So that's going to show you the difference. So it's not what you expect. So you are supposed to get Q, but you're on the incorrect program, you get 1. So this would help us detect this now. Very good. So we are in it together. I hope this example shows the importance of data flow testing, right? That helps you detect bugs that you would not detect if you only do edge coverage. Maybe asking what if I do prime path coverage, right? That is also control field. And I want you to try that. If you do prime path coverage, will that detect this? And where could you get into that? But anyway, I hope this is a good example to show that if you want to check, if you want to test, if the value of a variable is correct or not, you have to use it. And if you not use it, you're not going to detect it. Okay? And the data flow testing is typically considered to be pretty comprehensive testing. Okay? And as I mentioned before, it can be difficult to perform because like the pointers, okay, dynamic references, so that you do not know which variables you are really using, which variables you are really trying to define. And that really makes data flow testing practice can be challenging. But I hope that's an important idea for us to have. And sometimes when you write your code, if you want to make sure a certain computation is correct, you want to try to find an express that actually try to use the correct. It's an important approach to keep in mind. So we have discussed different coverage criteria, and that's what we keep to do. I hope by now you are kind of familiar with what we're doing now. We want to give you a hierarchy, okay, and so that you can make a choice depending on what kind of projects you have. So on the top would be complete path coverage. You want to test every possible path. Remember that does not guarantee program correctness. Okay, even you test all possible paths, you may not detect all the bugs that you have. We have seen examples of that, and we know that it's right path coverage. So as you can see, right path coverage is pretty strong, very comprehensive. Then you have 2 branches on the left branch. Okay. Is the data flow coverage. So all new path is stronger than all use coverage, and all uses coverage is stronger than depths. If you look at the definition, all depths only has each definition once. This one has every use of each definition. And this one has all possible new paths between the definition and use. So by definition, you can easily derive this relationship. Again, when I say one coverage is stronger than another coverage, it does not mean, okay, the stronger coverage will detect all the bugs. The weaker coverage can detect. It only says any test set that satisfies the stronger coverage also satisfies the weaker coverage. It's not about fault detection, even though it's likely, okay, a stronger coverage will also detect bugs that can be detected by a weaker coverage. You can only see very likely, it's not guaranteed. Okay? Because what bugs you actually detect depends on the values that you put in the test cases. So keep that in mind, what we mean by stronger. And on the right hand side, we have the control flow coverage that we discussed. Node coverage, edge pair is stronger than this one, and this one is stronger than. So remember, node coverage is basically statement coverage. Every line of code that you have written should be tested at this point. Edge coverage, every branch that you have in your code, you have to test what happens if that branch is stable. We have the edge case coverage that is stronger than edge coverage. So what is interesting is that you have this cross edge here. All uses coverage are stronger than edge coverage, and this I should mention that if you read the textbook, this has one assumption. It's the uses, like as I mentioned before. So if you look at the example here. So we have a branching node. What we have here, to simplify the discussion, I have annotated the depth set and the use set on the branching node. Like in this example, for example, node Q is a branching node. I have annotated that node. But what people typically do is that for P use, for practical use, you could also add the use set on the two edges. So it's basically for both outgoing edges of node Q, you're going to put the use set, okay, which is the same as what we had for the node on the two edges. Okay. As I mentioned before, like you could also annotate the edges as well. If you do that, then all uses coverage is stronger than edge coverage. Okay. So that's what how this cross relation comes from. You may be surprised. You do not consider like you do not annotate the branches, the branches of branching edges of the branching node. And also it's very interesting, it's prime part coverage is stronger than, I think it's easy to say this one. Okay. But prime part coverage is stronger than all new part coverage. Okay. And we have seen how to compute the prime part coverage. It's relatively simple to compute, relatively mechanical, and you do not have to do like analyze the dynamic references. That really simplify how you compute the testing requirements. So that's why like prime part coverage is used much more widely than what you part coverage. Actually, if you look at the second edition, the new edition of the textbook, it actually goes one step further. They say data flow testing is not really used in practice, at least based on their experience, based on their conversations with people in the industry. It's because data flow testing can be difficult to apply to those because dynamic references problem, and also because prime part coverage is stronger than DO part, and it's much easier for you to apply. So just need to put that in mind. But nonetheless, from academic perspective, it's important to know what the data flow testing is about. I don't know, I mean, from a certain perspective, you can consider that a program, okay, you can have an equation, a program equals data flow plus control flow, right? And that's what the program does. You make decisions, you access data structure, you perform computations. That's what the computer program can do. Okay, so that's why, like, when you test the program, you want to make the data flows correctly and you want to make sure the control flows correct. So to recap, graph provides a good basis for systematic test generation. Okay, and I just want to emphasize the key to testing. Okay, is really you have to be systematic. You cannot be ad hoc. Okay? You cannot say, well, because I like this particular values I could test. Okay. The problem with ad hoc is that you do not know what you have tested, what you have not, whether you have covered all the different bases. You know many bugs, okay, here at the corner cases. Being systematic allow you to so that you do not miss. Okay, because with ad hoc, you could easily miss some important pieces. Okay, so the key to get confidence, okay, the key to test the design is that you have to have a systematic strategy to select the test cases. And the graph is a good structure to use, okay, to guide the test selection so that you feel systematic. And the control flow testing focuses on how the control transfers, how you make decisions. Okay, and data flow testing focuses on data flows. We discussed control flow coverage that are defined based on nodes, edges, and path. Data flow testing. Data flow coverage is defined in terms of depth used. So any questions about control flow test and data flow testing before we move to a new topic, rapid testing? All right. I was on my way, driving on my way to office. Okay. I was listening to the NPR radio. So one of the things they were saying is that many people, like nowadays, they use YouTube to learn how to DIY, right? How to actually do it yourself. And what they start is that if you're like people feel in many cases they feel they have learned how to do it by watching the video, but when they actually do it, they get lost. So it's kind of like so the key point they actually conducted a study why this happens. So the point I thought very interesting is that they say watching is different than doing, right? It's just the same here. That's why we want to give you homework assignments. Like when you sit in the class, when you listen to what I say, it's different from like you do it yourself. I'm pretty sure that when you actually work on the homework assignments, you probably have more questions. but it's very important for you guys to work on those homework assignments. You can discuss with your fellow students, but really try to develop your own understanding and write down your own solutions. That's really indispensable. Practice is indispensable for you to actually learn. That's the point I just want to make. Okay. We're going to start a new topic, predicate testing. Okay. First, I want to give you some motivation. Okay, why we want to do predicate testing. So predicate, okay, it's a fancy name. As we mentioned it before, a predicate is basically a statement that can be true or false, right? So if we connect that to what we do when we write programs, right? So predicate is basically a decision point, right? A conditional expression that you use to make decisions in your program. Okay. So why we want to do predicate testing? Okay. So basically what we do is that in predicate testing is that we want to look at each decision point in your program. We want to make sure every decision point is written correctly. That's what predicate testing is about. Why we want to do that? Can anyone help me? Like why we want to make sure every decision point in our program. Every was decision point basically means if statements, while statements, right? When you have to make a choice, switch statements, those kind of branching structures. So basically we want to make sure every conditional expression is written correctly. Why want to do that? Yeah.
Doesn't it control the flow?
Yeah. Very good. As you can say, if you write a conditional expression wrong, your program is likely to be wrong, right? And from another perspective, what I typically put is that the intelligence of a program is basically encoded to a large extent in those decision points, because those conditional expressions that you write, basically they make decisions, right, in the execution of your program. They typically correspond to business decisions that you have to make in the application domain. So to simply put, those decision points are where the intelligence of your program is. Okay, and it's very important for you to make sure you make those decisions. Right? That is the motivation of behind predicate testing. And we will say predicate testing is actually very important. Okay, especially for those safety critical systems. Okay. So we have an introduction, basic concepts, and define different predicate coverage criterion, and we're going to say how we're going to actually apply predicate testing to programs. And predicate testing can be applied to specifications as well, but we're going to focus on how you can apply predicate testing in programs before we summarize. We pretty much covered this slide. And remember, predicates are just Boolean expressions that you will use in your programs to make decisions. Now we do program-based test, predicate testing. For example, this conditional expression inside the statement, that is a predicate, okay? Because it could be evaluated to true or false. And we want to make sure this condition expression is written correctly. That's what we're going to do. And when we generate test cases to make sure this conditional expression is written correctly. Now you can also apply that to specification-based. You can apply specification-based predicate testing. It's because when you look at those requirements, you can extract predicates out of the requirements and generate test cases for those predicates to make sure those predicates are actually implemented in the program in a way that is specific for the targets. And that's what I mentioned earlier. It's very important to do predicate testing. As you can see here, predicate testing is required if you're going to do business with the Omnis software. If you want to, let's say, you have your own company, software company, develop the software you want to sell to any airlines, right? You have to show them, okay? You have done predicate testing, you have to show the test report, okay, what test cases you have executed and what results you got from those test cases. And also, I really want to emphasize the philosophy. Okay? You build a product, okay? It's your responsibility to show the customer that you have done adequate testing and you have confidence about the correctness of the product. It's not like I build a product and I just let the customer figure out whether how the product is being made. And you have to show evidence to do that you have done adequate testing. The same applies to whatever code you write. Okay? I guess you write code, it's part of your job responsibility to test your code, to show the management that you have done adequate testing, to show the federal developers that you have done adequate testing before you give the code to other people, before you integrate the code systems. Okay, and that's a responsibility, right? If something goes wrong later on, okay, they are going to come back to your test report. You said, like this test case was executed correctly, and if that is not the case, after you integrate your system, you have to be able to explain, right? Otherwise, that's not really good for you. Okay, so that's a responsibility. That is why testing is important. Every software developer, every software engineer has to know how to test. Next, we're going to look at some basic concepts. So we have discussed the definition of predicate. Yeah. So to be more technical, the predicate may contain Boolean variables, okay, and also non-Boolean variables, but you have to somehow convert non-Boolean variables into Boolean value, right? The way to do that is that non-Boolean variables have to be compared with the relation output, because the relational expression will be a Boolean expression, will only have true or false. And then you could have Boolean function as well. And then you